Pleasant day to everyone. So in this lecture, we're going to discuss Module 7, the subject CE 3151, Numerical Differentiation. So to begin with, we define differentiation as a process of finding the instantaneous rate of change in a given function, which is based on one of its variables. And this instantaneous rate of change is what we call the derivative of a function, which is denoted in general form as dy over dx, or simply y prime, in which this is now what we call your first derivative. So given now a variable y, which is a function of x, if we take now the rate of change of variable y per unit change of variable x, we can now write dy over dx, which is now the difference of y values divided by the difference of x values, or the change in our variables. And we can now denote this as the slope of the given function.
From your calculus, we could derive now or define the derivative of a function using our exact solutions. So the exact solutions would basically involve the different rules applied in differential calculus or in differentiation. So we have the product rule. You also have your quotient rule, the power rule, and the chain rule. So these are the formulas that we use to directly solve for the derivative of a specific function and to get the exact value. While in numerical differentiation, we could solve now the derivative instead of using this equation. We'll now be solving through numerical differentiation approximate solutions or approximate values of the derivative of that function. So let's take into consideration this given graph consisting of 3 points. So the 3 points now will be defined in terms of its coordinates. So we have x, y coordinates, x and y, which is a function in terms of x. So we'll take point B as xi, and those after B will be xi plus 1 and so on. And then those points before B will be xi minus 1. So again, numerical differentiation or simply differentiation is simply solving for the rate of change of our function. So in this case, the rate of change, as we have said, is equal to the slope, which is delta y over delta x. So since point B is our initial point, x sub I, so solving now for the slope of AB, we solve this first, or the slope of point B. We solve first for the slope of AB, in which we will get our values from this shaded triangle. And then we also take into consideration slope BC, which will be taken from this shaded portion. So for slope AB, again, that's delta y over delta x in terms of point A and point B. So delta y now will simply be equal to fxi minus fxi minus 1. Okay, so this one is our delta y for AB, and this is our delta x for AB. Okay, so next we have slope BC, which is again in terms of delta y over delta x. So in this case, we'll now have this distance between BC as delta y for points BC, and this one is delta x for point BC. And that will now be denoted as So difference between this distance will now be f of xi plus 1 minus f of xi all over this point naman. So we have xi plus 1 minus xi. Okay? So if we're going to take into consideration now, we must make sure that the distances between our points along the x will be of equal values. Thus, delta x for AB and delta x for BC can now be called h. Okay? So with that, we could simplify now our derived equations for slope AB and slope BC as f of x sub I minus f of xi minus 1 all over h, and for BC, that will now be fxi plus 1 minus f of xi all over h. So another way to solve for the slope of B will now be in terms of the points that is before or and after the point B, which is now slope of AC. So if we're going to look at our graph, that will simply be, so we have A to C will now be fxi plus 1 minus fx minus I divided by A to C, which comprises of 2h. So if we're going to look at this, this is now the derivation of our equation for our numerical differentiation, in which for slope AB, this is what we call your forward, or your AB is your backward differentiation, since we are considering point B and the point before it. So pabalik, kaya sa backward differentiation. And for BC, this is now what we call your forward differentiation, whereas we now take into consideration point B and the point next to it, right after it. Okay? While for AC, we call this now as our central differentiation, as point B is at the center of our points. Okay? So with this derivation, we can now write this first derivative in different forms of the difference or differentiation. So for your 2-point forward differentiation, this was what we have derived a while ago using slope BC. 2-point backward differentiation is from our differentiation or derivation of the equation using slope AB, and the 2-point central will be from our derivation using slope AC. Okay? So for the other types of differentiation, the following formulas will be derived taken now from this value. So with this given x and y, if we note now x sub I as this value, okay, therefore the value before it will now be xi minus 1 and xi minus 2. So kung meron pa akong isang value before here, this will now become xi minus 3. Likewise, if my xi is 3, next value after this will be my xi plus 1 followed by xi plus 2 and so on, in which this would simply be 3, so yung value ng xi plus our h, or what we call the size step. Okay? So with this now, a 3-point forward differentiation will simply mean that we will be using the values of 3 points. So kung forward yan, I will be using xi, xi plus 1, and xi plus 2. So we have xi plus 1, and xi plus 2. And since, so kung i-graph natin, this is your xi, xi plus 1, xi plus 2. So we know that the difference between the points along x will have the same value. So this is from point xi to the third point will be 2h. Ito yun. Okay? So same goes xi, pag 3 point backward, xi, xi minus 1, xi minus 2. So this is also h. So from this point, xi going back to xi minus 2. So xi minus 1, xi minus 2 divided by the 2. Okay? So same goes. So pag 4 point central naman, so kung ito yung point ko, central, so siya yung center, so I will have 1, 2, 3, 4, 5. Okay? So with that, we will now have a 12 each value. Okay? So with that, let's have an example using our first derivative using numerical differentiation. So for example number 1, given f of x is equal to x squared, wherein we have values of x1, 2, and 3 equal to 0.5, 1, and 1.5 respectively. We have to find now the value of f1 prime at 1 using forward difference, backward, and central difference. So we have to determine, as we progress, the best method or the method that would yield the best result of the derivative. So in this case, what we are to find is f prime of 1, meaning 1 here is your x sub I. So we have now, beyond it is xi plus 1, and before it is xi minus 1. Okay? So before we start with our forward, backward, and central difference, we solve first for f of x. So using now this equation and the value of x, so just substitute the values of x in our equation. So 0.5 will have now equal to 0.25. So 1 we get 1, 1.5 squared we get 2.25. And from here we could see that the difference between the values of x, which will now be denoted as h, is equal to 0.5. So for our solution, so we have first our forward difference, which is given by this equation. So this is your forward. So we have now function of xi plus 1 that is equal to xi is 1, in which the function of xi plus 1 is equal to 2.25 minus the function of xi 1 over the value of h equal to 0.5. Whereas it will give us now a value of the derivative of x equal to 1 equal to 2.5. Then next we have our backward difference, which will have an equation of the function of x sub I minus the function of the x before it divided by each. So this one now is our backward equation. So for our f prime of xi, which is 1, is now equal to f of xi, 1, minus function of xi minus 1, we have 0.25. So divide this by each, 0.5. Therefore, by backward difference, the derivative now of x equal to 1 is equal to 1.5. Then, finally, we have our central difference equation. We'll have now f prime of 1 is equal to the function of xi plus 1, that's 2.25, so minus the function of xi minus 1, that's 0.25, divided by 2 times the value of each, which is 0.5, giving us now f prime of 1 equal to 2. So which of this following values is the best, or the result that would yield nearest to the exact value of our derivative? So we could check this using our calculus. So by power formula, so by power formula, we have now the function of x is equal to x squared. So therefore, f prime of x is equal to 2x, in which you take now the slope or the derivative when x is equal to 1. So that is 2 times 1, giving us a value of 2. So meaning the best, or the method that gives us the best result, will be through our central difference. So for our next example, we have the statistical rainfall data from 1990 up to 2010 is shown in the given table. So we are to find the rate of change of rainfall in 2000 using the central difference formula. So for the central difference formula, we have this given equation. So since we are solving for the rate of change of the rainfall, the rate of change here is your slope, that is dy over dx, or that is your y prime, and x I now will be equal to 2000. So in that case, you will now have your, so this is your value of x, this is the function of x, so 2000 is your x sub I. So using central difference formula, so we will need xi plus 1 and xi minus 1. So in this case, we will have now xi is to 2000, f prime is equal to 2000, that's equal to xi plus 1 is 698 minus x function of xi minus 1, that is 824, divide this by 2 each, in which H now is taken as the difference of the values of your x's that is now equal to 5. So this one is equal to 10. So that's 2 times 5. So with that, f prime, or the slope now, or the rate of change of rainfall for year 2000 is equal to negative 12.6. Okay, so for example number 3, we have the same value or given as for example number 2. So again, we have the year as our variable x. The rainfall data is our function of x. So this is our y. Okay. So what we want to solve for example number 3 is the rate of change. So again, rate of change is your slope or your dy over dx, or this is our y prime. So for the year 2000, so 2000 is your xi. And in here, we are going to use now the 3-point forward formula, which is given by this equation. So we will need now the following values. So to solve now, have f prime of xi, year 2000, and it's equal to negative function of xi plus 2. So this is xi. So we have xi plus 1 is xi plus 2. So we now have xi plus 2 will be the function of 2010 plus 4 times the function of xi plus 1, that's year 2005, minus 3 times the function of xi, which is year 2000. Okay? So we all divide this by 2 each. So 2, wherein each now is equal to 5. So substituting f prime of the year 2000 is now equal to negative 2010 is 657 plus 4 times the function of 2005, 698, minus 3 times the function of year 2000. So we have 7 and 5. So we divide this by 7. In that case, f prime now is equal to 2000, which is now equal to negative 25. So take note, if we're going to compare the rate of change of rainfall for 2000 is equal to negative 12.6. This is using your 2-point forward difference. So we have a large discrepancy between the two. So anyways, this is the value now for the 2-point forward, and this one is the value for 3-point forward difference. For example, number 4 is in the same given as for example 2 and 3. So we have now year as our variable x. The value of rainfall is the function of x, which is now equal to y. So we have established already that the difference between the x's, which is h, is equal to 5. So in this example, we are now to estimate the amount of rainfall. The amount of rainfall meaning the function of x which is for 1985. So the function of x for year 1985 ang hahanapin. And we are going to use the 3-point backward difference with xi equal to 1995. So xi is 1995. So backward difference, so before it is xi minus 1. 3 points backward, so meaning we will have to need 3 points. So we only have xi minus 1. So we'll need a value of xi minus 2. So in this case, xi minus 2 is equal to the year 1985. So for the 3-point backward difference, the equation now that we are going to use is this equation. So if we're going to substitute, we will have f prime of 1995 is equal to 3 times the function of xi. So function of xi is 1995 minus 4 times the function of xi minus 1, that's 1990, plus the function of xi minus 2, 1985. So we divide this by 2 times each, which is 5. So from our given, we have now the value of f95. 95 is this value. We also have f of 1990. And so we have now two unknowns, f 1985 and f prime of 1995. So to solve for this, so two unknowns, one equation, so we still need one more equation. And in this case, what we can solve is the value of f of 1995. So we solve first for f prime of 1995, and we are going to use your central difference. So for central difference, f prime of 1995, which is your xi. So we will need now, center is 1995. So before and after will now be equal to f of 2000 minus f of 1990 divided by 2 each is 5. So that will now be equal to f of 2000, 795, minus f of 1990, 892, divided by 10, and we will get a value of negative 6 point, or that's negative 9.7. So this value will now be substituted in this equation. So if we're going to write now our value, so f of 1995 is negative 70. That's equal to 3 times function of 1995 minus 4 times the function of 1990 plus the function of 1985. Divide this by 2 each. So we only have one unknown. So the function now of year 1985, or the rainfall for year 1985, will now be equal to 999. So this is our final answer. Okay, so that's for the first derivative. So next we have The second derivative, so we'll have a different set of formula for the second derivative for different types of differences. In this case, for the second derivative, minimum number of points will be 3 points, unlike for our first derivative, which will have a minimum value of, or minimum number of points of 2. So we also have your forward, backward, and central derivatives or central equations. Okay? So basically, we'll have the same process. You have here your xi, so xi minus 1, xi minus 2, so we have xi minus 3, and so on. So we could also have set this as, so if we have here as xi, then we have here xi plus 1, xi plus 2, and so on. So these are the values that you will need. And since it's a second derivative, take note that the value of each is always squared. Okay? So to understand or to have an application of the different equations for the second derivative, let us have. So for example, number 5, we calculate the second derivative at x equal to 4 with h equal to 0.35. So using the 3-point central difference formula for the function given, 3 raised to x over 4x. So since we're using the central difference formula, so it means that x equal to 4 is your x sub I. So x sub I plus 1, and x sub I minus 1. X sub I is 4. So we have h is 0.35, so means we have here 4.35, and we have here 3.65. So substituting now the values of x in this equation, we get now the function. So for 3.65, that is now equal to 3.7769. For x equal to 4, f of x now is 5.0625, and for 4.35, its function of x is equal to 6.8380. So for the formula, for 3-point central difference for the second derivative, we have this equation. So you just simply substitute your values of f of x. So we get now the second derivative of xi, 4, is now equal to the function of x plus 1 minus 2 as the function of f of x sub I plus the function of x I minus 1, that is 3.7. So we divide this by each 0.35 squared, get now f prime, or the second derivative, and f double prime of xi equal to 4 will give us now 3.999, or this is approximately equal to 4. So that's for our differentiation.